Welcome to Inorganic Chemistry. Today we are going to explore the fascinating world of relative orbital energies. We will discover exactly how electrons choose where to live inside an atom and why this simple choice shapes the entire universe around us. By the end of this video, you will understand the hidden rules that govern the periodic table. To understand how electrons behave, imagine you are moving into a massive futuristic apartment building. Naturally, everyone wants to live on the lowest floor possible because it takes much less energy to walk up the stairs. In the microscopic world of atoms, electrons behave exactly the same way. The nucleus acts like the ground floor, pulling the negatively charged electrons inward. The atomic orbitals are like the apartments, and each one has a specific energy cost or rent associated with it. Relative orbital energies simply tell us which orbitals are the cheapest and which are the most expensive. Now that we have an intuitive picture, let us look at the formal definition. In a simple hydrogen atom, there is only one single electron. Because there are no other electrons to interact with, the energy of an orbital depends exclusively on its principal quantum number, denoted by the letter n. This means that the 2s and 2p orbitals in a hydrogen atom have the exact same energy. Chemists refer to orbitals with the exact same energy as being degenerate. But what happens when we add more electrons into the mix? This brings us to multi-electron atoms, where the situation becomes much more complex. When multiple electrons are present, they start repelling each other. This electron-electron repulsion, combined with how well the inner electrons shield the outer electrons from the nucleus, changes the energy landscape. The energy of an orbital now depends on both the principal quantum number n and the azimuthal quantum number L. As a result, the subshells within the same principal level split into different energy levels. The s orbital is generally the lowest in energy, followed by p, then d, and finally the f orbital is the highest. Before we look at the math, let us understand why this concept matters in the real world. Understanding the relative energies of orbitals is the absolute foundation of all chemical behavior. It dictates the Aufbau principle, which is the rulebook telling us the exact order in which electrons fill empty orbitals. This filling order determines the electron configuration of every single element on the periodic table. Because an element's chemical properties are controlled by its outermost, highest energy electrons, these energy levels explain everything from why metals conduct electricity to why noble gases are completely unreactive. Now that we know why it is important, let us look at how we actually calculate these energies. To figure out which orbital has a lower energy, chemists use a simple mathematical guideline known as the Madelung rule or the n plus L rule. This rule states that the relative energy of an orbital is directly proportional to the sum of its principal and azimuthal quantum numbers. In this formula, E represents the relative energy. The symbol N stands for the principal quantum number, which indicates the main energy level or shell distance from the nucleus. The symbol L represents the azimuthal quantum number, which defines the shape of the subshell. If the sum of N plus L increases, the energy of the orbital increases, meaning it will fill with electrons later. Let us see this formula in action with a concrete example. A common point of confusion is why the 4s orbital fills with electrons before the 3d orbital, even though 4 is a higher shell number than 3. Let us use the n plus L rule to prove mathematically why the atom behaves this way. First, we need to calculate the value for the 4s orbital. We identify the principal quantum number, n, which is 4 because it is in the 4th shell. The azimuthal quantum number L for any s orbital is always 0. Continuing with our calculation, we take these two numerical values for the 4s orbital and substitute them into a simple addition formula. Adding 4 and 0 gives us a total energy index value of 4. Next, we do the exact same process for the 3d orbital. The principal quantum number n is 3. Because it belongs to the third main energy shell. The azimuthal quantum number L for any d orbital is always defined as 2. We now have the pieces we need to find the sum for the 3d orbital. Now we substitute the values for the 3d orbital into our addition formula. Adding 3 and 2 gives us a total energy index value of 5. Finally, we compare the two results. The sum for the 4s orbital is 4, while the sum for the 3d orbital is 5. Because 4 is less than 5, the 4s orbital has a lower relative energy. Physically, this means an electron will experience less repulsion and be more stable in the 4s orbital, which is exactly why it fills before the 3d subshell. This formula we just used leads us to an important question. What happens if the sums are equal? Sometimes calculating the n plus L sum for two different orbitals gives you the exact same number. This creates a mathematical tie, which can seem like a dead end. To resolve this, we must apply the official tiebreaker rule. The rule states that when two orbitals have the same n plus L value, the orbital with the lower principal quantum number, n, has the lower energy. Let us look at an example to see exactly how the atom decides. Let us determine which orbital has the lower energy between the 2p orbital and the 3s orbital. First, we will calculate the sum for both orbitals, just like we did in the previous example. For the 2p orbital, the principal quantum number n is 2, indicating it is in the second shell. The azimuthal quantum number L for a p orbital is always 1. We will plug these two numbers into our formula to find the sum for the 2p orbital in the next step. Adding 2 and 1 together gives us a total index value of 3 for the 2p orbital. Now we look at the 3s orbital. The principal quantum number n is 3, placing it in the third shell. The azimuthal quantum number L for an s orbital is always 0. Substituting these values into the formula and adding them together also gives us a total index value of 3. Both orbitals have an n plus L sum of 3, creating a mathematical tie. We must now use our tiebreaker logic. According to the tiebreaker rule, we must now look at their principal quantum numbers. The 2p orbital has an n value of 2, while the 3s orbital has an n value of 3. Because 2 is less than 3, the 2p orbital wins the tiebreaker. Therefore, the 2p orbital has the lower relative energy. Physically, this means the 2p orbital is closer to the nucleus on average and offers a more stable environment for the electron, so it fills with electrons before the 3s orbital. Now that we have used this formula and the tiebreaker rule, let us look at a visual summary of these calculations. What you are seeing here is the Madelung diagonal rule diagram. It perfectly maps out the increasing energy levels we just calculated. Notice how the diagonal arrows trace the exact filling order. The arrow passes through 1s, then 2s, then 2p followed by 3s, exactly as our tiebreaker predicted. It then goes through 3p and 4s before finally looping back to 3d, just like our first example showed. This diagram is a handy shortcut for the n plus L rule. We have covered a lot of ground today, so let us review the most important ideas. First, the relative energies of atomic orbitals dictate the architecture and behavior of the entire atom. Second, in multi-electron atoms, these energies are beautifully governed by the n plus L rule, which accounts for both distance and shape. Finally, by simply adding these quantum numbers and using the lower n value as a tiebreaker, you can confidently predict the energy ranking of any orbital. You now hold the master key to unlocking electron configurations and understanding chemical reactivity. Great job!